In this video, I will review the remote sensing information that we discussed last week. Remote sensing is the procurement of information about an object or phenomenon without making direct physical contact with that object. This is different than in situ observations, which are on-site observations that can have direct or close contact with the objects. Remotely sensed images, a form of raster data, can be taken from a variety of platforms such as planes and UAVs, as well as balloons, rockets, kites, telescoping poles, among others. The data that is collected is processed and assigned a value to each pixel that represents a surface on the Earth, kind of like color by number. The process of remote sensing most often begins with the sun producing light. However, this is not always the case. It depends on whether the sensor is active or passive. Passive sensors do require light from the sun, but passive sensors do not. Active sensors actively gather data by emitting electromagnetic waves of their own in the form of light as in radar, radio waves as in radar, and sound waves as in sonar. In both active and passive sensors, electromagnetic waves make their way to the Earth, are reflected off the Earth's surface, and are then transmitted to the sensor. Passive sensors only use the electromagnetic waves from the sun. After active sensors emit their own light, sound, or radio waves, they wait for the wave to return and then can calculate the distance between the ground location of the pixel and the sensor. The different wavelengths are recorded as pixels in a piece of remotely sensed imagery. In the image on the slide, you will see the term spectral signature. Each different type of an object, such as tree cover or bare soil, has its own unique spectral signature, which allows us to identify it and understand the geographic variation within an image. The recorded imagery is then processed and converted to a usable form where we geographers use it to better understand spatial phenomena. Depending on what you're analyzing, you will want to make sure that you have certain wavelength bands, which is based on the electromagnetic spectrum. In the slides from last week, I gave you a bit of a cheat sheet of examples when each band is used, so I will not go into detail about that today. The electromagnetic spectrum is a continuous range of electromagnetic radiation that ranges from highly frequent short wavelengths to long wavelengths with a low frequency. The spectrum can be divided into 7 different parts, including gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. Humans can only detect the visible light portion of the spectrum. They can all be measured in terms of frequency, wavelength, and energy. Frequency is measured as the number of crests or troughs that pass a point within 1 second. Wavelength is measured as the distance between the crests or troughs. Wavelength can also be measured as the distance between the troughs instead of the crests. Imagery sensor bands are based on the electromagnetic spectrum. Each band consists of a range of wavelengths or frequency values or a portion of the spectrum. A panchromatic image consists of only one band, and it's usually in grayscale. The brightness of a particular pixel is dependent on the intensity of the solar radiation reflected by the objects and then received by the detector. Multispectral and hyperspectral images consist of several bands of data. Each band can be displayed one band at a time or in combination of 3 bands at once, which is called a color composite image. The difference between multispectral imagery and hyperspectral imagery is in the number and width of the bands. Multispectral imagery usually has 3 bands, 3 to 10 wider bands such as red, green, blue, near infrared, and shortwave infrared. Hyperspectral imagery has much more narrow bands, about 10 to 20 nanometers, and could have hundreds or even thousands of those narrow bands. The quality of remote sensing data consists of its spatial, spectral, radiometric, and temporal resolutions. Spatial resolution is the pixel size in a raster image. Spectral resolution accounts for the wavelength of the different frequencies of the bands that are recorded. Radiometric resolution is the number of different intensities of radiation that the sensor can distinguish between, including the number of levels of grayscale and color shades within each band. Temporal resolution is the frequency of the flyovers by a satellite or plane over the area and is really only relevant when the data includes multiple recordings over time.